I'll start off with a little bit of review of what we've been doing, because we're building up to connecting limits to derivatives, which is like, this is calculus. This is what calculus is all about. So first, we took 2 points on a curve and made a secant line with point A and point B, and we started off with saying 1 point is X, 1 point is A. And we actually made X get close to A, and we had this formula then for the slope of the tangent at A. And when we use this formula, as we did in an example like this, since we're finding it at the point 2, 1, we plugged in 2 for A, and we said we're looking for when does X get close to 2. And as this secant line got closer and closer, we found out that the slope was equal to 6. And every time we've done it so far, and every time it will work out this way, the non-permissible value canceled out, then we could apply the limit, plug in 2.
Sorry for the interruption. All grade 11 and 12 French immersion students who are attending the festival.
Then we changed the formula and did the same formula again, but we did it with a different idea. Instead of taking the point X and A, we took the point A and said the horizontal distance is H. Then if I move H to the right, this point B would be A plus H. Just a different way of looking at the same thing. And then the formula, instead of X approaching A, we now say H approaches 0. And when we did an example with this, right, we had our formula, but now our point was at 3, so we would plug 3 in for A. And just like before, things simplify nicely. Your H eventually cancels out. Then you could apply your limit, and we found out the slope was equal to 6 in this line. Today, we go to what mathematicians like to do more often. They say, instead of starting with a specific point, like A is equal to 3 or A is equal to 7, let's just start with something in general. Let's just start with X. So we have this same idea. Here's my curve. Here's my point A, and A is just some random point, X comma f of X. We take a second point B, and we use the second idea with H so that we can call this point that's not much room there. That second point would be X plus H, and the Y coordinate would be f of X plus H. Right? Then our formula and our derivative with both of these formulas, instead of plugging just an A.
Okay, everybody, water's back on in the building, so all is good. Have a great day.
Instead of just plugging in a specific point A, we can actually plug in a variable X. And the difference will be, instead of finding a specific slope, we can find a formula for all of the slopes. So we can easily find any one. Instead of having to do the formula over and over and over again, we'll get a formula for all of the slopes. So this is called the definition of the derivative, sometimes called Newton's quotient, because this is how Newton came up with the idea. Okay? And it can be written in 2 different ways. We've seen the 2 different strategies, but now instead of a specific point, we're going to be looking at the general idea. Just right at the top, answers not on site, will be by Mr. J. one time only. And then prick your finger into the thumb print. Oh, I'm still, oh, I muted it. Okay. Yeah. All right, here's the notations for the derivative, okay? We have very common, if you're using function notation, they put a little dash in between the f and the x, and we read it as f prime of x. If you're just using y notation, you put a little dash behind the y and go y prime. And if you're using y notation, you can use Leibniz's notation. So this is more f prime of x is more Newton's notation. Leibniz said dy over dx. The d is sort of like a delta, almost like a change in y over change in x. So it gets that idea of slope, and that was Leibniz's notation. Can also be used if you start with y equals. Again, the notations, Newton's notation is probably used more when you're doing derivatives because it's quicker, right? Instead of having to write 1, 2, 3, 4, 5 things, you just write 2 things, and the second thing is just a tiny little dash. So it's a little bit quicker. However, there are places that Leibniz's notation actually helps us more. So the notation is kind of interesting that we still have 2 notations because they're both helpful in different places. So now what we have to do is we have to use our skills and limits just like we've done before. We're going to use our algebra, sometimes multiplying by the conjugate, sometimes factoring, right? Plug it into the formula. We want to simplify, and our goal is to factor out an h, because there's going to be an h on the bottom that makes it unable to solve the limit. We want to factor out that h so we're no longer dividing by 0. And then we find the derivative. And what we're going to find is a formula for every single slope at every single point on the parabola. And that's going to be way more powerful than just those first 2 formulas. I'm going to ask you them on the quiz. When I ask you them on the quiz, I'm going to be specific which formula you need to use. And because I'm being specific in which formula you need to use, I have to give you the formula. So those 2 formulas you won't have to know. This formula you will have to know. Here's the definition of the derivative formula with an x. Okay? Again, every time you're thinking of derivatives, I want to make sure that you can go back to the basic idea of I have 2 points, and this is point A, which I will call x comma f of x. This is point B, which, if I make that part h, then point B will be x plus h, because I've moved over h to the right, comma f of x. And all the definition of the derivative is your slope, which is rise over run. Can you see that if I took f of x plus h minus f of x, that would be my y value. And h is my x value. And I want to bring that point B closer to A, and as I get closer and closer, my secant line gets closer and closer to the tangent line. And it's so simple in a lot of ways. And it ends up being so powerful for a lot of mathematics. Like sometimes when you start introducing calculus and it's like, all it is the slope of a tangent line. Like, I spent 12 years of school math to get to just, that's it? That's all calculus is really looking at? That's so disappointing. I've been misled. I want to sue the Manitoba Teachers Society. But I think that's also part of the beauty of mathematics is that a lot of ideas, when you break them down, are just that. There's something simple and elegant and beautiful for that reason. So what does that mean for this equation, right? This is our standard parabola. This is what we're imagining. And I want to find a formula so that if you pick a random point on here, right? Here I pick 2, 4. There's the tangent. What's its slope? What if I pick, choose a different color, -1, 1. There's its tangent. What's its slope? So prior to today, we would have done one of the two formulas and found it from those formulas exactly. The problem with that prior to today is we would have had to do the equal amount of work for 2, 4 that we would have to do for -1, 1. Right? And then if I wanted to find another one, I'd have to do all that work again. Today's plan is to use the definition of the derivative to get a formula that finds all of them. And I'll show you what it looks like. So we're going to find the derivative. It's going to equal the limit as h goes to 0. F of x plus h means that in your function, you replace remember how functions work. The way that a function works, f of 1, you plug in 1 for x. Even if there was lots of x's. F of 7, you would plug 7 in for x. Even if there was lots. F of w, you plug a w in for x. And so if we have f of x plus h, you would plug in x plus h for the x, and that would give you x plus h squared. Then we subtract f of x. Well, f of x was just the original function, which was just x squared, all divided by h. And our goal is in the numerator to be able to factor out an h so it cancels out, so we can apply this later. So we start saying, well, what could I do? Well, I could either factor this as a difference of squares or maybe expand the x squared plus h. Right? If I expand x plus h squared, I will get x squared plus 2xh plus h squared. Remember, you have to multiply it all out, do all the arrows, distribute, FOIL, if you like that word in English. Minus x squared all over h. This gives me the limit as h goes to 0 of, and we notice that my x squared minus x squared cancel out. And then the two terms that I'm left with, they both have an h. So I'm going to factor that h out. And those h's cancel, which is what I wanted because now I can apply the limit. The limit is, plug in 0 for h, is just 2x. And this is powerful, because that is now a formula for all of these slopes. If I go to the blue line, what's my x value? My x value is 2. The slope of this line is 4. I just plug in 2. I go to the red line. X value is -1. The slope of this line, plug in -1 into my derivative, is a -2. I can find any slope almost instantaneously using the definition of the derivative. And now I've created a formula for that. So they ask in part B, oh, what's f prime of 3? Well, on my graph, can you see that you would have the point 3, 9 way up there? You'd get a pretty steep slope at that point. F prime of 3, I just have to plug in 3 into my derivative formula, which is 2x. So f prime of 3 is equal to 6. And what does this mean? The slope of the tangent line at the point 3 comma 9 is 6. But this is way more powerful because now once you do this once, I can find any slope of any tangent anywhere. And it's fascinating that it made such a simple formula. So we get questions like y equals 3 root x. So I'll start by writing out the formula. The limit as h goes to 0 f of x plus h minus f of x over h. Now in the formula uses function notation. You know that anytime you have an equation y equals, if you wanted to, you could replace the y with f of x, because f of x and y are the same idea, just different notations. So in this case, my function even though it was y equals, I can think of it as 3 root x. Okay? Eventually, you won't write out the definition. You will probably start off with this. This would probably be your first line that you would write. You would go, okay. I could just write out the definition, but actually apply it to the formula that I have. So the formula that I have, I am going to, here's f of x. First of all, I'm going to replace that x with x plus h. So I have 3 root x plus h minus 3 root x over h. And this is why we do the practice with limits to begin with, because we want to be able to solve these limits. And you might recognize, oh, what did we do when we had a bunch of square roots? We wanted to get rid of square roots. What would get rid of square roots? Well, if you took this and multiplied it by a difference of squares, then it would simplify and the square roots would go away. So what can I multiply by here? I could multiply by 3 x plus h, and because it's a minus, I will multiply by plus 3 root x on the top, and I will also multiply by that on the bottom. What does that do for me? I get the limit as h goes to 0, and on the top it becomes this squared minus this squared. Now if I square this first one, can you see that you would get 9? And then the square root squared would just become x plus h. Minus, and I square this one, it'll be 9. And the square root of x times square root of x will just be x. And on the bottom, I'm going to leave that h factored out. Again, the reason behind that is because we want that h to cancel out. So leaving it factored out makes sense. Something beautiful always seems to happen. 9x minus 9x, they go away. You're left with just 9h on the top. And this is the most satisfying part of this question. When you get to that point where you can cancel that h out, and you now know that you can apply the limit. Because I can now plug in 0 without any consequences. Well, I don't even have to write limit anymore. I can just go equals. Because I apply the limit, I'm going to get a 9 on the top. And on the bottom, I have 3 root x plus 3 root x. Those are like terms. And I get 3 over 2 root x as my derivative. Straightforward, simple. And this is the formula that finds any of our slopes. So let's see, graphically, can we imagine our original equation, 3 root x? Okay, I'm going to review some of your transformations from last year. Do you remember what the square root graph looks like? The regular square root graph, which I'm just going to do in a dotted line here. Right? This would be your regular square root graph. It has important points like 0, 0, 1, 1, 4, 2. Again, you can find them just by plugging in numbers. That 3 out in front would have been a vertical stretch. So the graph that we were dealing with, which I'll graph in blue, would still have 0, 0. It would have 1, 3 instead of 1, 1, because the vertical stretch would have multiplied your y values by 3. And instead of 4, 2, it would have 4, 6. And I can now find, like, oh, at 1, 3, what's the slope of that tangent line? Well, if I want to find the slope of that tangent line, the x value is 1. Go to my formula. The slope of that line would be 3 halves. Take a different one. What about at 4, 6? There's a new tangent line. Well, the x value is 4. I could plug 4 into my derivative formula. Square root of 4 is 2. I would get a slope of 3/4. And so the powerful thing about Newton's definition of the derivative, Newton's quotient, is that you can find a bunch of them quickly. Whereas the first 2 formulas that we did, you have to do the process over and over again. They're nice to start off with because they give us a specific idea. And dealing with specifics is usually how mathematicians start. They start with specifics. And they're like, oh, this is cool. But wouldn't it be nice if I could create a formula that would do this faster? And they move from specifics to general, and that's what the definition of the derivative is. So again, for us, dy dx, that's our derivative, different notation. It's going to equal the limit as h goes to 0. Newton's notation works nicer for the formula. It's the problem with Leibniz's notation. Function notation works really nice with the formula because it tells us what we have to plug in. Can you see that if I think of this as f of x equals 2x cubed plus 4x, now when I replace something in my function, there are 2 x's in the equation. So if I ask you what's f of 2, you'd have to plug in 2 twice. If I ask you what's f of 7, you'd have to plug in 7 twice. When I ask you what's f of x plus h, you're going to have to plug that x plus h in for every x. And this becomes limit, h goes to 0, and things are going to get quite big here. I'm going to have x plus h cubed plus 4x plus h. I'm going to put a big set of blue brackets around that, minus, and another big set of blue brackets around that. Because we have, first set of blue brackets is f of x plus h. The second set is f of x. This is all over h. So a lot of higher level math is also, can you hold a lot of data and remember all of the things that you're doing as you're going along? I put those extra brackets around because here, if I'm subtracting all of this, I'm subtracting both of those. That's going to be important. Okay? Now, in the next step, are going to expand this. Okay? I'm going to first, and maybe you want to put this off to the side somewhere, I'm first going to talk about this. But I want to talk about this off to the side because I'm going to write the answer to this right in the equation in my next line without showing a lot of work. I'm going to do the work for this x plus h cubed off to the side. So x plus h cubed means x plus h times x plus h times x plus h. And your job is to write out what that's equal to expanded. So you have some options, okay? Option 1 is, what should I do as option 1? Option 1, I will go with the oldest method that you would know how to do, is if you went back to grade 10 math and had to do this. In grade 10 math, you would take 2 of these and multiply them first. X plus h times x plus h is x squared plus 2x h plus h squared. Yes. And then multiply by another x plus h. And if you multiply by this other x plus h, you would have to distribute the x, distribute the h, and you would probably, if I distributed the x's, I would get x cubed plus 2x squared h plus 8x h squared. Then if I distributed the h's, I would have plus x squared h plus 2x h squared plus h cubed. Then I would look at this and go, oh, I have some like terms there and some like terms here. I can combine those like terms. And get x squared plus 3x squared h plus 3x h squared plus h cubed. Or I could, from grade 12, do you remember Pascal's triangle for the binomial theorem? Because it's a cubed, you know that you would have 4 terms in the expansion. We've got all 4 here. The coefficients will be Pascal's triangle 1, 3, 3, 1. Then you would start with x cubed, go down by 1 with your x's until there was none left. Start with 0 h's, then go up by 1. And you would get the same answer directly. So whichever way, and you can see why I didn't want to do this math right underneath the line because it's busy. Well, all I wanted to do in our next step is say 2 x cubed plus 3x squared h plus 3x h squared plus h cubed plus 4x plus 4h. And for right now, for your visualization, I'm going to keep that in the blue brackets so that you can see that the blue bracket that I had initially has now turned into this. And we would minus 2x cubed and minus 4x. All over h. Okay. And now the nice things start happening. I want you to notice that the 4x is going to cancel out with 4x. And when I multiply this 2 by this x cubed, it will cancel out with that. So what do we have left? What we're going to have left is a 6x squared h, a 6, here I'll write it, 6x squared h, because that's when I multiply this by this. I will have plus 6xh squared plus 2h cubed plus 4h. Wow, that's pretty good. All over h. And And every single term in our numerator has an h. So we can factor that h out. Get 6x squared plus 6xh plus 2h squared plus 4. Yes. Success. No, I don't. Okay. Oops. Sorry. I can now apply the limit. So you have to write limit as h goes to 0 all along until you get to the point where you can now I can plug in 0. So now that I can plug in 0 for h, a bunch of things go away, and I'm just left with 6x squared plus 4. How long did that question take? Way too long. Oh, but it's just like it was nice, enjoyable math all the way along. If we look at view, and we here we go. Zoom entire page. It took long because of this x cubed part. Took a while for us to review how we would do that. Okay. And a fair bit of algebra needed to be done, but the h's canceled out. So it might have taken us, we could check on the video later, 5 minutes, 7 minutes, 10 minutes, okay? Next unit, it took us 10 minutes. Next unit, we are going to learn a technique for this question that will save us a little bit of time. And by a little bit of time, I'm going to tell you about, off of this 10-minute question, we are going to save 9 minutes and 58 seconds. Unbelievable. Like if that took us 10 minutes, right? As soon as, maybe even more, I can tell you that for those of you that have done this before, Abby and Alice, they looked at the question, and before I even wrote dy dx, they knew the answer 2 seconds in, maybe even a half a second in. They just looked at it and knew the answer was 6x squared plus 4, which is going to be also beautiful. But we have to, with mathematics, we have to start with, where did the ideas come from? The idea that this came from was limits, and a limit is a slope, rise over run, and we have to develop the limit to find the answer. But, as with mathematicians, as soon as they start doing something, they look for patterns, and mathematicians found patterns in the derivatives, which will, like I said, if this took us 10 minutes, shave off 9 minutes and 58 seconds. Unbelievable. Can you imagine if they could do that for schooling? Right? It takes you 12 years of schooling to graduate. 9 minutes and 58 seconds is percentage-wise is like almost 99%. Can you imagine coming into kindergarten? 3 minutes later, here's your diploma. I think you could have done calculus, but you went to Central, that's okay, but here's your diploma in 3 minutes. Somebody else is like 3 minutes later, sorry, you have to go to credit recovery. Oh, here's your new diploma. Credit recovery done half a second later. That would be crazy. That would be like if all of a sudden they said, okay, you're born, we are going to replace your brain with a hard drive, and then you have a little USB port off to the side. Welcome to school. They plug in a USB, download. All right, you're good to go. That would be crazy. Right? The parents would be there at kindergarten. My imagination is going crazy right now. Parents would be there at kindergarten going like, okay, we're going to sit through this. Oh, car mechanic. I wouldn't have seen that 30 seconds ago, but And I guess their interest kind of went that way. It's, wow. But, so we haven't figured that out yet for people in schooling. I would be out of a job. It'd be like 3 minutes later, oh, teacher, here's your welfare check. You can't do any work anymore because we have made your job obsolete. All right, one more example to go. This one would take a little bit longer with a shortcut, right? This one's going to take us 10 minutes, and we'd only probably shave off 8.5 minutes, 9.5 minutes, 30 seconds it would still take us. But here we go. F prime of x. I'll rewrite out the formula every time for now. That's just your slope formula. And plugging things in, we would have x plus h plus 2 over 2 x plus h minus 1 minus x plus 2 over 2x minus 1 all over h. So things look awkward to begin with. Yes. We have to think, well, what is the math that I know? What can I do? Well, I'm subtracting fractions. I have a fraction inside of a fraction. So just like in identities, one of the greatest strategies you can do is, can I simplify this just so that it is a single fraction? On the top, if I want to subtract those fractions, I would need a common denominator. What does that common denominator look like? Well, this one is missing a 2x minus 1, and this one would have to be multiplied by a 2x minus 1. This one is missing a 2x plus h minus 1 and a 2x plus h minus 1. And so and I would lose a half a mark because in the next step I forgot to write the limit part. I have to write that every single time until I can apply the limit. So next line, limit, as h goes to 0. On the top, can you see that you now have a common denominator? 2x plus h minus 1 times by 2x minus 1. On the top, I'm going to multiply things out. So here, I'm going to multiply this out. I'm going to keep it in brackets. I'm going to keep my subtraction sign, and I'm going to keep this in brackets. If I multiply this 2x by everything, I'm going to get 2x squared plus 2xh plus 4x, and then if I multiply the minus 1 by everything, I'd have minus x minus h minus 2. Same thing in the second one. Maybe in the second one right now, are you okay if I write this as 2x plus 2h instead of 2 bracket x plus h? Just so that when I multiply it out, I'm going to multiply the x first. So x, I get 2x squared plus 2xh minus x plus 2x plus 4h minus 2. And this would still be all over h. So one of the things that calculus will also do for you is re-practice all of your algebra skills. This one has lots of fraction work, algebra skills in it. Okay? And we have to be careful. Do it at, if you think I could do this at this speed, whatever speed you think you could do it at, I suggest toning it back, do it at half speed. Because if you try to do it a little bit fast, or even at regular speed, we're humans. How many calculations are we doing? Lots, right? What are your chances, like, how good is your mental math? 99%? That means you make 1 error in 100, right? If you go a little bit faster, you increase that to 2 errors out of 100, right? Every error that you make in mental math, in a question like this, probably will add 10 to 15 minutes to the question. Every mental math error. Did I make one? You think so? Which one did I make?
4x instead of 2x.
In the second one, 2x squared, 2xh minus x plus 2x. Oh, this would be plus 4x. See? Oh, I would love to say I did that on purpose. But that would have caused all sorts of problems moving forward. So, this is what actually drives a lot of people away from math. Because it's not that you don't have the capacity to do the math, you just make every single time 1 error. Which then, when you check your answer at the back of the book, every single time, they say you're wrong. Right? They don't say, oh, you made a tiny error. You know what you're doing. You just made a tiny error. You're fine. No, the textbook translates to you're wrong. So you try another one. You're wrong. You're wrong. And so your confidence is just beaming at that moment because over and over again, you've been told you're wrong, you're wrong, you're wrong, you're wrong, which makes math frustrating. Usually, you are mostly right. You know what you're doing. And when I point out the mistake, it's like, oh, did you know that 2 times 2 wasn't 2? It's actually 4? Like, absolutely. I know that 2 times 2 is 4. But I wrote 2. That happens. So we have to go at half speed to solve. And then when you get the shortcuts that you save 20 minutes off these questions, awesome. So, okay. So where are we at? Limit. As h goes to 0. We've got our big line, that's h. Our next line that has 2x plus 2h minus 1 times 2x minus 1. And on the top, this minus sign is going to get distributed through all of this. We are going to combine some like terms, but I'm going to imagine. I know that there are some like terms in there, but I'm going to imagine doing all of this at once. First of all, I'm going to notice that my 2x squared and my 2x squared is going to go away. Okay? I'm going to notice that my 4x and then minus my 4x will go away. My x and minus a negative x will go away. The 2xh and the 2xh will go away. And all I'm left, and the minus 2, oh, this is enjoyable. What initially looked like it was going to be terrible now. Now what am I left with? I'm only left with a minus h. Minus 4h will give me minus 5h. Wow, that was nice. Okay? Because at this moment, as you are writing this out, your brain will start to tell you, is this really what I should be doing? This is too much writing. And then this one, okay, maybe we're onto something. This is feeling better. Now, the bottom I can think of as a fraction as h over 1, right? So then I have a fraction divided by a fraction. I can multiply by the reciprocal, so this would be the limit as h goes to 0. My top fraction, negative 5h over 2x plus 2h minus 1. 2x minus 1. Multiplied by the reciprocal, 1 over h. And all of that to get that final h to cancel out. I can now apply my limit. This is going to equal -5 over, and maybe you can see on the bottom it'll be 2x minus 1 all squared. Beautiful. Wonderful. Now, just for fun, let's look at the original equation and see if you remember how to graph this. Because we're going to say, what did we just figure out? So a little review from grade 12. Grade 12, if you were asked to graph this rational equation, I hope that you can see that there's a non-permissible value when x is 1/2. Right? Because plugging in 1/2 would cause us to divide by 0. So what that means is that that non-permissible value, the original graph at 1/2 would have an asymptote. Now you learned this in grade 12 pre-calculus, but we've also learned this for limits. When x gets really big, in other words, if I took the limit as x to infinity, can you see that the limit as x to infinity is also going to be 1/2? That means that we will have a horizontal asymptote at 1/2. In grade 12 pre-calculus, I would have said, can you find the x-intercepts and the y-intercepts? Yes. Y-intercept is really easy because you plug in 0 for x, and you will get 2 over -1. So your y-intercept will be 0, -2. And your x-intercept would be plugging in 0 for y. Plugging in 0 for y means I would have 0 equals this fraction. And anytime you have 0 equal to a fraction, the only way a fraction is equal to 0 is if your numerator is equal to 0. Technically, I mean, okay, so this is what I have. So I'm going to say, from a holistic point of view, I can say the only way a fraction is equal to 0 is if the numerator is equal to 0. When is my numerator equal to 0? At -2. -2 comes. Mathematically, you technically, if you wanted to solve this, you could multiply both sides by 2x minus 1. Doing that would just leave you with 0 still equal to the numerator. And then you could subtract 2 on both sides and solve. So having those 2 points will tell us that our graph from grade 12, you would have said, oh, this part of my graph has to look like this. And if I wanted to find the rest of the graph, I would probably plug in a number. Like if I plug in 1 here, on the bottom, I'll get 2 minus 1. On the top, I'll get 3. So I would have also the point 1, 3. And if I have that point and my asymptotes are there, this is what my graph would look like. And what we just figured out is by finding the derivative, if I am interested in this tangent line, that's when x is 1, I could plug in 1, and I could find out the slope of this line is -5. If I want to take this one here at the x-intercept, at -2, I could plug in -2. I'd get -4 minus 1, which would be -5. -5 squared would be 25. And I would get the slope of this line to be -5 over 25, or -1/5. Which is, like, we found a formula to find any slope at any point. And what a slope is at a point is an instantaneous rate of change. If we go back to some of our definitions, we are finding how fast is the curve changing at that point. How much is its slope at that point? All right. So there are some questions from your textbook at the bottom there.